Okay, let's move into the next chapter now, chapter 11, the shapes of molecules. Recall we've been doing Lewis structures to look at where the electrons are in the molecules and all that type of stuff. Now, how can we get a Lewis structure and from that determine the shape of the molecule? What does it look like in 3 dimensions? All right, and the theory that tells us what molecules look like is VSEPR theory, valence shell electron pair repulsion theory. Some people call this VSEPR theory. I don't care for that, but some people do. I just say VSEPR. All right, and VSEPR is really pretty easy to understand. There's a couple of little intricacies here, but in general, it's this simple. Electrons are negatively charged. They repel each other, and so if 2 clouds of electron density, if 2 electron groups are repelling each other, how do they get as far apart as possible? And that's all this is about, is how do 2 electron groups on a central atom, on one atom, get as far apart as possible. A few things to note when you're dealing with VSEPR theory, we're looking at bonding pairs of electrons on that central atom, lone pairs of electrons. And VSEPR theory treats double and triple bonds as one group. So even though a double bond has 4 electrons in it, it is one group repelling the other groups. Because you cannot separate the 4 electrons from each other in a double bond. You can't move a double bond, have one part of the double bond on one side of an atom, one part of the double bond on the other side of the atom. That cannot happen. Both parts of the double bond must be bonded to the same atom, so they must be on the same side of the central atom. This will become more obvious as we go through it. But let's go through the stuff. Let's start, for example, BeCl2. That's 16 electrons in this molecule. If you do the Lewis structure, you find it looks like this. This is another one of our incomplete octet molecules. Beryllium is fine with just 4 electrons around it. So when we look at this, we've got the beryllium as our central atom, and we have the 2 chlorines as the terminal atoms, and the question is, how can we get these 2 groups maximum distance apart in terms of angle? Well, it should be obvious. If you've got 2 groups on a central atom, the maximum distance apart is 180 degrees from each other. 1 chlorine on one side, 1 chlorine on the other side. And that's what we find. And we call that, unsurprisingly, linear geometry, because chlorine, beryllium, chlorine, all in a straight line. So 2 groups coming off a central atom, that's a 180 degree angle, that's linear. Note, look at carbon dioxide, and if you do the Lewis structure for carbon dioxide, you find, okay, it looks like this. Note, this carbon, it has its octet, but here's a double bond, here's a double bond. VSEPR theory treats double bonds as 1 electron group. So here's 1 group of electrons, here's 1 group of electrons, maximum apart, 180 degrees. It is also a linear molecule. But now let's look at BF3. If you have 24 electrons, if you do the Lewis structure, you find that this boron, also an incomplete octet, but it is fine to have the 3 fluorines around it like that. And so note, we've got 3 bonding pairs on that central atom. What's the maximum distance apart in terms of angle? Turns out it's 120 degrees. This molecule is trigonal planar. Trigonal because there are 3 groups coming off that central atom. Planar because it's flat. It's a completely flat molecule. Okay. Well, let's look at this beast, NO2- with 18 electrons. If you do the Lewis structure for NO2-, you get this, and you'll say, uh-oh, yeah, you did the Lewis structure, you did everything right, but then we had a double bond on this oxygen, a single bond to this oxygen. What makes this one so special that it can have a double bond? Nothing, so we know we have resonance forms, which means there's no real double bond, there's no real single bond. Both bonds are the same length, roughly a bond and a half or so. The good news about VSEPR theory is it does not matter which resonance structure you choose. Just choose one of the resonance structures because the answer will be the same for any individual resonance structure or the resonance hybrid. The actual molecular resonance hybrid has the same geometry that you would get from any one resonance structure you might care to look at. Okay, so knowing this, we look at, here's our central atom nitrogen. How many electron groups coming off of it? Well, we've got that single bonding pair. That's one. We've got the double bond, but the double bond counts as just one electron group, so that's two electron groups. The single is one, double bond, one electron group. And the lone pair, that counts as an electron group, so that's three electron groups on there. The single bond's one group, the lone pair is one group, the double bond is one group. How do you get three electron groups as far away from each other as possible? That's right, trigonal planar again. So this is a trigonal planar geometry. But somebody said, you know what? Okay, I see that it's trigonal planar, but do we really count the lone pair when we're looking at the geometry of the thing? Shouldn't we just really look at the atoms? Because I can see with this BF3 right here, I can see that being trigonal planar, no problem, because I've got three groups coming off that, three atoms coming off that boron. So someone decided to do this. Okay. When you're going to name the molecular geometry of the molecule, we're going to ignore the lone pair. So we come with two terms now. The electronic geometry is what we call it if we do not ignore the lone pair. We say, okay, the electronic geometry for this is going to be trigonal planar because we have three groups coming off that nitrogen. The double bond group, the lone pair group, and the single bond group. Three groups coming off that central nitrogen, so that will be trigonal planar electronic geometry. But if someone just asked you, what is the shape of this molecule? And that was the only thing they told you. What is the shape of this molecule? They are talking about the molecular geometry where we ignore that lone pair. Note, when we draw it out with the electronic geometry, we have to say, okay, trigonal planar because there's three groups, but we're going to ignore this lone pair right up here, just ignore it, and say, okay, what is this shape? What is this shape of this O and O? And we call it bent. Okay, bent doesn't sound very scientific, so some people will call it angular. Angular sounds much more scientific. I myself call it bent. Okay. Something to note that it turns out these lone pairs take up just a little bit more space than bonding pairs do. Because note, if you got these two electrons in this bond, the nucleus of this nitrogen is kind of corralling the electrons towards it, attracting electrons towards it. The nucleus of this oxygen is also pulling the electrons towards it, which means these two electrons here, this nitrogen is kind of pulling electrons towards it, but up here there's really nothing pulling electrons towards it. The way people kind of indicate it sometimes is they say, okay, this cloud of electrons, see how it's kind of ice cream cone shaped or something like that? There's just a lot more space up here, so this is going to tend to push on these guys a little bit. This is taking up a little bit more space, so one would normally think that this oxygen, nitrogen, oxygen angle should be 120 degrees. It's probably just a little bit less than 120. No, not that much less. We're talking like maybe 118 degrees or something like that instead of 120. But lone pairs take up just a little bit more space than bonding pairs do. And truthfully, when you look at a molecule like this with 120 degree angles, there's really very, very little difference between the molecular geometry angle, maybe 118 versus, say, 120. So there's very little issues when you're looking at these trigonal planar based geometries such as bent, but we're going to find with other molecules it gets a little bit more pronounced. Okay, let's look at our next molecule, CH4. We do the Lewis structure for CH4. We got the central carbon, the four hydrogens around it, and what's the maximum distance they can get away from each other? Now your first thought might have been to draw it, and I bet on the paper when you drew CH4 you probably drew it like this. with the 4 hydrogens coming off like that. And that's fine on paper, but if we do that, we note that this angle, any angle here, is 90 degrees. If this molecule were flat, those would be 90-degree angles. But hey, these molecules are three-dimensional. We don't have to keep them in a flat plane on the paper. And so it turns out in three-dimensional space, the best way to get 4 groups that are repelling each other maximum angle apart is a tetrahedral arrangement, which has a 109.5 degree angle. Now, on a flat piece of paper, it's a little difficult to draw a tetrahedron and have you know what it looks like, and so we've decided to do it this way. This carbon, we've got just this normal line to this hydrogen, which means this hydrogen is coming straight up like that in the plane of the paper. This hydrogen here is going down and to the left, but it's still in the plane of the paper. See how this line is drawn as a wedge? This wedge means this hydrogen, while it's coming kind of down, it's kind of coming towards us a little bit. If I could make this pen into that carbon-hydrogen bond, it would be coming out like this. So it's not flat in the paper like this, it's coming down away from that carbon, but kind of out towards the viewer a little bit, out towards us a little bit. And that's what that wedge there means. The dashed line on this back hydrogen right here means that this one is going down, but going back. It's going like back into the plane of the paper. It's going backwards away from us. Just as this one was coming forward towards us, this one's going back away from us. But the interesting thing, the geometry tells us that this angle is 109.5. This hydrogen-carbon-hydrogen angle is 109.5. This guy going back, carbon, this hydrogen coming out angle, it's all 109.5 degree angles. Okay. Well, in the next video, we'll start looking at some examples.